University, una institución de Universidad Complutense de Madrid, and also the University of Extremadura. So we are presenting here the structure of grammatical evolution for predicting hypoglycemia events for people with diabetes. So I will explain briefly what is diabetes and hypoglycemia. I will also give some details, basic details about the structural grammatical evolution and the results we have with this problem. So diabetes is a group of diseases characterized by a high level of glucose in the blood, resulting from two main types, depending on the body problem to produce insulin, which in this case we are talking about type 1 diabetes. What is the most? Is me or is okay? And in the case that we have our resistance to the insulin, we are talking about type 2 diabetes. In both cases, it is necessary to control the levels of glucose in the body, in the blood, and we need to perform different types of prediction for helping people with diabetes to manage the disease. And especially the people need to control and to have the level of glucose in healthy levels that is usually established between 70 and 180 milligrams per deciliter. And we need to avoid, or it's very important to avoid the conditions for complications that are usually for hyperglycemia and for levels below the 70 value, which is the hypoglycemia. It's important to maintain these levels in the range because we can have, or the people with diabetes can have not only long-term complications but also short-term complications. And the short-term complication can even depend in the diet of the people with diabetes. So in this case, we treat one of the most important parts that this is hypoglycemia. So as I told you, this is occur usually when the people with the person with diabetes inject insulin, and the amount of insulin is not the appropriate. So it can depend in the episode of hypoglycemia. And as I told you, if this episode is too long, the person can have health problems. So our objective here is to give a tool to people with diabetes, and we try to obtain prediction models for hypoglycemia events based on the information that a diabetic has usually at the time of prediction. And that is usually a continuous glucose monitoring system that is nowadays spread on the population with diabetes. Give us a measure of the glucose value every 15 or 5 minutes, depending on the brand, on the model of the continuous glucose monitoring system. And also, we include information from smart watches such as a Fitbit here or an Apple Watch. And also, we have more variables, but we selected 3: the heart rate, the steps, and the calories obtained with these devices. We tackle the problem as a classification problem, and for this we adapt the structural grammatical evolution by Lorenzo and Pensal Machado made in the past, and we adapt it for a classification problem. And we obtain, as I told you, the data. We perform a feature augmentation including historical information of the variable we have. After this process, we perform also a selection of the features after a correlation study of the variables and eliminating those that are more correlated. And with the selected features, we implement a grammatical evolution classification modeling. Just briefly, grammatical evolution is a variant of genetic programming that is guided by a grammar that give us the possibilities of the expression we are going to generate. Here we can see an example of grammatical evolution for symbolic regression that is usually used as genetic programming tool. The main difference with classical genetic programming is that we need a mapping process from the genotype to the phenotype of the solution. The process is a bit complicated, no, not complicated, but not easy to explain in 2 minutes. But the idea is to use a map function to map each of the genes with the grammar and to obtain an expression. So we started from the initial point. In this case, we call it start. And using the genotype, we select the expression that more adapt to the problem we have. For instance, in the first case, we have a 0. So the first gene is a 0. We start from the start point, and we have 2 options. We can go for an expression or for a terminal. And as it's a 0, we apply the modules and we go to the expression. And so on, we can decode all the expression and finally obtain, in this case, a mathematical expression for symbolic regression. Grammatical evolution has also some features, some characteristics that can be a drawback in the evolutionary process. Mainly, is due to the appearance of disruptive crossover. And for dealing with this, as I told you, Nuno Lorenzo and Pedro Machado designed the structural grammatical evolution, which is a variant that tries to make this crossover process more, let's say, more ordered than the simple grammatical evolution. And the tool they use for this is to include in the genotype a set of lists that indicates the maximum number of terminals that we can go with each non-terminal value. Again, it's not so easy to decode, but the main difference is that we control how the crossover is made. There are 2 variants of structural grammatical evolution, the static and the dynamic. The static, those lists that are used to control the crossover are static and are generated at the beginning of the evolutionary process, just analyzing the grammar. This can go for longer lists and being less efficient. In the case of dynamic, those lists are dynamically generated through the evolutionary processes, and depending on the step and the number of terminals that are waiting for the coding. As a genetic programming genetic programming algorithm, the problem with dynamic is that it's prone to bloating, so both has its advantages and drawbacks. So we perform an evolutionary process, typical evolutionary process, and we use a fitness function for classification and adapt the grammar for this. Here you can see an example of the grammar. The grammar is instead of an expression as I put to you in the first slides. You can see here that we are going to, in the first line in the grammar, we are looking for an expression that at the end gives us a classification of the event. So we, depending on the value of the glucose, finally we obtain a classification of the event. Or a 0 will be a hypoglycemia event, and a 1 will be a non-hypoglycemia event. And we use a fitness function, the weighted accuracy, in order to reduce the number of false negatives. That is what the most dangerous part in this classification. So we train prediction models for different time windows, for 30, 60, 90, and 120 minutes, which is usually the time windows that people with diabetes need to have in advance. So the objective is at a point of prediction, we use the information we have from our smart devices, and From this, we have also the historical values and perform a prediction if in the next 30, 60, etc. minutes we are going to have a hypoglycemia event. Another advantage of this method is that we obtain explainable and implementable expressions. Here we can see an example of one of the solutions where we have the variables that we can analyze. One of the things, for instance, is that in most of the solution we have the glucose at the time of prediction, which is expected, which is the most trustable value for making the prediction. So in practically all the models we obtain the glucose, so it's correlated with the idea we have at the beginning. And then we also obtain expression that can be interpretable, although not always being something expected by the medical staff. But finally, we can analyze what are the variables that are more influencing the models. We have here the results for 30 minutes. Similar results are obtained for different time windows, of course decreasing in quality when we go for longer time windows periods. Here we present results for 11 patients. Just to note that it's not easy to obtain the data from the patient. These are real patients from our hospital, because we need the commitment of the person with diabetes to fill all the data. Then we need the commitment of the medical staff to give us in a good format the data, and also we need to deal with the missing data that can appear as a fail in the smart device or whatever. So, well, we need a lot of time. Now we have 25 patients. We're preparing a bigger work with this. Here we can see the results of the recall values of the classes, which is the most important in our case, for the best individual after 30 runs. With this, we obtain values for 30 minutes close to 95% of accuracy in the prediction. And here we can see the evolution of the average population for 60 minutes prediction horizon. And we can see that we obtain an evolution in the process almost up to the end of the maximum number of the generation that we established at 500 generations. In the box plot, we can see a comparison between the static and dynamic structural grammatical evolution. Although the numbers can say that the dynamic is a bit better, but statistically it's not significant. It's not significantly statistically the difference. So we can say that they work almost in the same way. As a summary for the different time horizons, we obtain an average recall for the 30 runs and the different individual, the different patients for 30 minutes between 90 and 95%, and decreasing through the increase of the time windows. But even for 90 minutes, we obtain a 90% in some of the patients as an average for all the models. Another thing that we can see in the paper is that the models are almost robust because the variables that appears in the models are usually the same. So the model, we can say, are robust in this sense. So now we are working on adding more patients to the test. We are also analyzing the data of the patients in order to search for clustering of the individuals and of the situation that the people with autism has. We are also including now more information. This first approximation was intended to avoid information that is difficult to evaluate at the time of prediction, such as carbohydrate and insulin injections. But we are including now in the models we are dealing with this information we collected in the past. Of course, we are also working to predict with other states, for instance, the hyperglycemia, which can be treated in a very similar way. So this is all. Thank you for your attention. If you have any question.
Great talk. Are there any questions in the audience? No. Okay. But I have some. I was wondering if you have considered doing this as an online optimization process, so that because I was thinking that probably the prediction will be very different from patient to patient because they have a different metabolism.
Yeah.
So do you think it's possible to do that in an online manner, that it gathers data over days and then what kind of converges to the patient-specific model?
Yeah, we have specific models and general models. And we have an application, a mobile application, for that the user can train their own models or use a general model. The general models are thought for people without the data initially, so we use at least one model. And then you can generate model not only for hypoglycemia, but also for the time series prediction of the glucose. And we use different techniques. With the group of Extremadura, we are also working on a different process with images for predicting hypoglycemia, and also we use neural networks and fuzzy logic. So we have different techniques.
Okay, interesting. Thank you. Any other questions? Then I got some more. I was wondering if there is a way that doctors currently do it. Like, can they predict such events from their experience, or like what other parameters they observe?
No, this is a very good question. It's not easy to predict an hypoglycemia, especially if the patient has usually hypoglycemia events. Because, I mean, it's something like losing some conscience. So if you have the habit to have some loss of conscience, then you are not noting the hypoglycemia. So this is one of the main important things. So we try to generate alarms in the smartwatch for this kind of events.
Thank you. Well, if there are no other questions, then I can close the session. So thanks again.
Thanks again
to the speaker, and